Okay, Chapter 8, Section 2, Area of a Surface of Revolution. A surface of revolution is formed when a curve is rotated about a line, usually the x-axis. Such a surface is the lateral boundary of a solid of revolution. So if the surface area is A, we can imagine that painting the surface area would require the same amount of paint as does a flat region with the same area A. Here's a quick example. As a simple example, let's say that we had a very simple little shape that's formed by taking the line y equals to some constant, like this. So let's say that this goes from there to there. So from some value a to b along the x-axis, and that this line is just a line segment that represents some function. Let's say, just to make up a number, let's say this represents 5. So this is the line y equals to 5 from x being greater than or equal to a, but less than or equal to b. So it's like a little line segment. And now what we're going to do is we're going to take that and rotate it about the x-axis. So if we think about rotating about the x-axis, we get something that looks a little like this. Okay, so it looks a little like a cylinder or a pipe. And remember, in this section, for the surface of area, we're only interested in the skin of this pipe that comes this way over here and then rotates to the other side. We're not interested in this side over here, right? There's the open end. You can think of this as sort of an open end like a pipe. We're not interested in the red or the red back there. That would be the other side. We're only interested in the skin of it in this direction. If we wanted to paint it, what kind of surface area would it be? So, for example, it would look something like this. Once I rotate that cylinder on its side, it would look a little like this. It would have some sort of a radius, right? If it's being spun from the x-axis, you can imagine that the x-axis would come, this way and come through the center of it. That guy, and then come this way. So this could be the x-axis this way. Okay, so it's going to have some sort of a radius. And so the perimeter, the circumference of that circle there, this is equal to 2 pi r, right? Circumference of a circle. So that would be this part here. Let me highlight it in yellow. That would be this part here, and then reaching out to the back there. That highlighted yellow part has a circumference of 2 pi r. Now if we cut it this way and roll it out, then that highlighted yellow part becomes this length, right? Like a long piece of paper, and we just curl it up, we can get this sort of a shape. If we cut it and roll it out, we would get a shape like this. And then the height, h, is this one, which is of course the same as this one if we cut it over here. And then when we roll it all out, it turns into this one. Okay, so we can see that the surface of this rectangle is going to be length times width. So here we can see that this area here, is equal to the length times the width, which in this little scenario, the area then is equal to h times 2 pi r. And then, so in this context, when it's all rolled out, we think about it as an area. Whereas over here, this is exactly the same thing we're looking for. It's the surface, the area of the surface of this three-dimensional shape, which is equal to this. Okay, so just moving it around a little bit is how they get this little formula here, that A equals to 2 pi r h, 2 pi r h. Good, and so that's the area of this surface. Okay, so the area of this cylinder. Okay, well, we want to work with shapes that are a little bit more complicated than this, so we got to develop a nice formula that can help us figure out the surface area of shapes that have curvature to them. Okay, so now let's take a look at a circular cone with base radius r and slant height L. Here the radius is this right here. So we can think of it as coming out from the center, sort of the base of this, right? The base of this cone is the circle. So the radius of that circle in the base is lowercase r. And then the length, the slanted height of this, or length of this cone is represented by this L. So it goes from there all the way down to the bottom. Okay, so if we take this ice cream cone kind of shape and we cut it along this dashed line and roll it all out, we would end up with getting a shape that looks like this. And of course, the perimeter of the circle at the bottom, starting from here and then kind of traveling this way, from there all the way around this way, and then through the back. There. So the perimeter of that red thing, well, that's going to be the formula 2 pi r with this as the radius of this circle, which then becomes this. When we roll it all out, it becomes this surface right there. Right? So this surface, this perimeter becomes that one right there. And then the L that we cut this way becomes the radius of this new circle, right? So this is a segment, a sector of a much bigger circle. So we have like two circles we're dealing with. We have this circle, which is formed when you make your cone, and then we have this sort of second circle that's a much bigger circle. It comes this way, goes back that way, and sort of looks like this. And so in the big circle, this becomes the radius. The radius of this new larger circle is L, which over here used to be the slanted height of our cone. And then this is the angle of our sector, theta, in this larger circle. Okay? All right, well, let me refresh your memory a little bit about circles, if you recall. A couple of important properties of circles. So in a circle of radius r, the length s of the arc that subtends a central angle of angle theta in radians is equal to s equals to r theta. In particular, if you divide both sides by r, we get that theta equals to s over r. So if we have a circle, not necessarily the unit circle, any circle, then the angle theta is equal to the length of the arc s divided by the radius r. So we get s over r. Okay? So that's how, coming back over here, we can get to this formula. This angle theta is going to be equal to 2 pi r divided by L. Right? Remember, don't confuse the r. This is the radius of this circle over here, whereas now in this larger circle, L becomes the radius of the larger circle. Okay, so we get an angle theta. Next, we're going to be interested in finding the area of this flat surface, this blue, because the area of this sector over here, this flat area here, is the same as the surface area of this cone that we're interested in. And so again, if you remember, hopefully back in your pre-algebra days, that if we have a slice of pizza, a sector, and we want to find the area is equal to this formula. Area equals to 1/2 r squared theta. Okay, 1/2 r squared theta. So now if we come back over here and we want to find the area of this segment, so using that formula right there, we get that the area of this blue region here, area is going to be equal to 1/2 radius times radius radius squared times the angle like that. And we're dealing with this of the larger circle, so that means that the radius is L. It's going to be an L squared, 1/2, times, and then the angle theta, which is equal to the area we're interested in. Okay, but we already established from the other formula that the angle theta is equal to 2 pi r divided by L. So then the area is equal to 1/2 times L squared times 2 pi r divided by L. And now one of those L's reduces. This one reduces with that one, so there's only one in the numerator. And this 2 reduces with that one. So the only thing that survives is a copy of L, a copy of pi, and a copy of r, which gives us a very nice formula for the area of a surface of a cone. Let's say surface area of a cone. Surface area of cone with radius r and slanted height L, the way we have it there. That area is equal to pi RL, right? A very straightforward, simple little formula that gives you the surface area of a cone like this. Next, let's consider a similar situation. Let's say that we have a cone and we want to find the surface area, but we don't want to find the surface area of the entire cone. We want to find the surface area of a portion of that cone, the surface area of this partial cone thing like this. Okay, so we already established that the entire surface area of a cone, right? So let's say surface area of cone. We said it was this really nice little formula, pi RL. But now let's say that we have a cone like this, and we want to find the surface area of this shaded part down here. Okay, how are we going to do that? Okay, so here's the game plan. Let's figure out the area of the entire cone, including the empty part, the whole thing, the surface area. That's an easy formula. Just follow that. And then we're going to subtract away this empty cone. Okay, so the area we're interested in, let's call that A. A is going to be equal to the entire cone. So the entire cone is just going to be pi, and then the base of the large cone that has an R2, so that would be R sub 2 times the slanted length, and the slanted length is going to be the sum of these two values. So it'll be equal to L sub 1 plus L, right? These are L's, by the way. L sub 1 and L. Okay, so this gives me the surface area of the whole big cone that has this base R sub 2, all of it, all the way to the top. That's just following this simple formula. And then from that, we want to subtract away the part we don't want, the surface area of this empty cone up at the top there. And that one, well, it's still pi R sub 1, right? Of the empty cone, the radius of this empty cone is R1, R sub 1, times L sub 1. Like that. Okay, so this difference will give us the result that we want. Okay, let's simplify this a little bit by factoring out the common term of pi. So A equals to, there's a pi, then like a giant bracket. And now distributing the R2 and combining the both terms that have an L sub 1, we get R sub 2 L1 plus R sub 2L minus R sub 1 L sub 1. And now bringing these two together, we'll get the following. Let me scroll down here. We'll get that A then is equal to pi giant bracket, r sub 2 minus r sub 1, factoring out an L1, and then there's a plus r sub 2L. Okay, so all I did was combine this term and this last one. I kind of wrote them right next to each other and factored out an L sub 1. That gives me r sub 2 minus r sub 1, and then brought this off to the side. Okay, so we need a way to simplify that a little bit. And to do that, let's come back up here and take a look at our picture. So if we think of this, picture, we can identify that we have two similar triangles. One is formed up here with these values in sort of the empty cone. We have a triangle right here, goes this way. So right angle comes up here and then comes across this way. And then another one is going to be the large triangle that comes all the way down here. Again, forms a right angle here, and it comes all the way out to there. Right, so this giant triangle with this hypotenuse. Okay, both triangles have the same corner up there, so they share that corner. Both triangles have a 90 degree. Therefore, we can conclude that that third angle must be the same for both of them. This angle must be the same as that angle. And so we have similar triangles. Because there are similar triangles, then we can conclude that L1 divided by R sub 1 is the same, is equivalent to this length, which is the summation of L sub 1 plus L divided by R sub 2. So we can say that L1 divided by R1 is equal to L1 plus L divided by R sub 2. Good. Now we multiply both sides, cross multiply, we end up with R sub 2 L1 equals to R1 L1 plus L. And now distribute, we get R sub 2 L1 equals to R sub 1 L1 plus R sub 1 L. Bringing this term over to the left, we get R sub 2 L1 minus R sub 1 L1 equals to R sub 1 L. And now we can factor out an L sub 1, and we end up getting R sub 2 minus R sub 1 L sub 1 equals to R sub 1 L. Now this looks exactly like that. So we're going to take this equation and plug it right into there. So I'm just going to move it over here to have a little more room. So from over here, put it over here. And I'll say that A, I'm just going to copy that little formula, A equals 2, and then there's an R sub 2 minus an R sub 1 L1 plus R sub 2 L. Okay, and so now I'm going to plug in this right into there, and so we get that A equals to pi bracket, and then this becomes R sub 1 L plus R sub 2 L, and they both have an L, so we can factor it out, and so the area of this sort of partial cone is pi L times, and then the sum of R sub 1 and R sub 2, R sub 1 plus R sub 2. So that's my favorite form of this equation. I think it looks pretty neat this way. So if you want to find the surface area of this cone, but not the entire cone, just a portion of it, so a partial cone surface area, then the formula is pretty neat. It's equal to pi times L, the length that you're interested in, and then we just add these two radius. That's pretty good. But one more thing you could do, your author also likes to use this formula, A equal to pi L, and then this new R, where R, oh, sorry, there's an extra 2 in here. So your author likes to go one step further and do the following. If you take pi L and throw in a 1/2 R sub 1 plus R sub 2, like that. Of course, you can't just introduce a 2, so you're going to have to multiply it by 2, so that this 2 and this half cancel each other out. And now this can be rewritten as a new value R, which represents sort of the average of these two, right? If you add two numbers and divide them by 2, you get the average. So another way of representing this area would be A equals to 2 pi L R, no subscript, where this R is equal to 1/2 times R sub 1 plus R sub 2. That's the other way that this formula is sometimes seen. Personally, I like this one better, but you should be aware that this is also pretty popular. Okay, so this is where we're heading with this. Let's say that we have this function here, some f of x function, and then we want to rotate it about the x-axis. So let's say that we have, y-axis there, and we have the x-axis here. Actually, no, let's make it a little closer. The x-axis here. We want to rotate this about the x-axis, so maybe this goes something like this. Okay, well, I'm not a great artist, but you get the idea. It's going to be this three-dimensional shape that gets rotated like this, and we're interested in the shape, the surface area of this shape. Okay, how are we going to approximate smooth curvatures? What we're going to do is go back to the previous section and think about approximating the length of a curvature by doing a bunch of straight lines. So we might have a straight line that connects from there to there, a straight line that connects from there to there, a straight line that connects from there to there, and so on and so forth. So in the previous section, we saw those approximations, and they looked a little like this. Okay, so they look a little something like this, where that curvature, that f of x blue curvature, is approximated by all these straight lines, these little straight lines. So now when we rotate just the red ones now, when we rotate them, we would get a shape that's similar to the one over there. Right? So this one would come this way like this and come that way like that. Except instead of having smooth edges, we'd end up with a bunch of sort of straight lines. So this one kind of relates to that one. And then maybe the next one kind of comes in a little bit like this. And then I guess the next one also kind of comes in a little bit more like this. And then the next one kind of comes out. And then the next one comes out. Okay, so you get the idea. These jagged ones begin to form this sort of a shape, like this. All right, well, you get the idea. So there are going to be a bunch of sort of flat edges that begin to approximate this smooth one over here. And what we're going to do is we're going to look at each one separately. So if we look at this first one over here, this first one is going to have just this part here. So the edges are the straight red lines from there to there, and they connect this straight line here. And then from there to there, just that part there. And then we're interested in the surface all the way around, right? So this looks like the surface area of a partial cone. If I was going to continue this, it would look something like this. right? So it's like one big cone, but then we just want a portion of it, which we just looked at formulas for. Okay, so my pictures are pretty ugly. Here's a nicer rendering of this same thing. Okay, so here's a better rendering of the exact same thing. Suppose that this curvature here, f of x, is given. So rotate the curve y equals to f of x um, for the segment x trapped between a and b about the x-axis. Okay, so here is a and b on the x-axis. We're going to rotate it around, and it creates this three-dimensional shape that almost looks like a vase. And we want the surface area. Remember, we're not interested in the caps, the area of the circle at the bottom where you would sit this base, or the area of the circle at the top. We're interested in the skin of it. We want that surface area, and it's got this smooth, curvy edge to it. So the way we're going to do this is by approximating it with a bunch of line segments. So let's say that here we're gonna approximate this curvature here by a bunch of straight lines. So for example, this little straight line here would be a little line that connects something like over here from there to there, for example. And then when we rotate it, we end up getting this sort of a shape where this is a straight line there and there's a straight line over here. So then this looks like the surface area of a partial cone, right? Just like the things we've been working with. And if we extend the sides of this little band, it'll look just like a cone. Maybe this kind of goes out to like around there. You see how if we extend the sides all the way out to there, we can think of this tiny little segment as a little piece of a cone, and we already have a formula for that, right? And if we come up with another band, so let's say another random band, so very roughly constructed here, this could be another band in green where I'm connecting this point to that point, creating that little segment there, this point to another point, say around there, and then there's another line segment here. And then if I extend those out in this direction, again, we have this green cone in this direction. And again, we have the surface area of a little piece of that cone, a band of that cone, which could be this part over here. Okay, and we can keep going, and together all these little bands of cones, all these little pieces of cones can be glued together to give you an approximation to the actual surface area that we're interested in. Okay, so now let's spend some time clearly defining how we're going to create an equation to approximate this surface area using these little straight edge bands of cones. So in order to define its surface area, we're going to divide the interval from a to b into n subintervals with endpoints x sub naught, x sub 1, dot, 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 all the way out to x sub n. So in this image here, that would mean that the A would be the x sub naught, and then right next to it would be x sub 1, and then x sub 2, and so on and so forth, so on and so forth. And then the very last one out here would be x sub n. Okay. Each one of these would have an equal width of delta x. So the width right here will be delta x. And then if I went out to the very last one, x sub n, right before it is x sub n minus 1. X sub n minus 1 would be that guy right there. And the little gap between those is still going to be delta x. Okay, now let's look at somewhere in the middle, right? We got x sub naught, x sub 1, x sub 2, dot, 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 dot. Somewhere in the middle, we'll observe the x sub ith level. that guy. And the one that came right before it would then be the, let's put it over here, just to have a little bit of space. The x sub I minus 1 value would be right there. And the width between them would still be delta x. Now I know I drew it really big here, but that's just because it's a little easier to see. But all these delta x widths are actually supposed to be the exact same. And remember, delta x is supposed to be really small. Okay, so now if y sub I is defined to be the value of our function when you evaluate it at x sub I, that means that this point here is p sub I, right? So p sub I is an ordered pair that's right there that represents the ordered pair x sub I, comma, f of x sub I. And so this point over here, which is the result of this one, let's put a line there, from there to there, that line right there. So then this is the ordered pair x sub I minus 1, comma, f of x sub I minus 1 is also equal to p sub I minus 1, and that refers to that point right there. And both p sub I minus 1 and p sub I are points on the surface. Good. Okay, so if y sub I equals to f of x sub I. Okay, so now what we could do is think about this height here. Just notation. So it would be maybe just that height right there could also be referred to as y sub I. Y sub I is that height right there. And then likewise, over here on this side, we can think of this height here, there, as height y sub I minus 1. This is height y sub I minus 1. And of course, y sub I, in this context here, this means that it's the same thing as the output of f evaluated x sub I, and y sub I minus 1 is the same thing as f evaluated x sub I minus 1. Okay, so we have a little band that's created, right? So then the side of that band is this right here, this segment connecting this point to that point. And then when we rotate it, we'll have on the other side another flat connection over here connecting these two. Okay, so if y sub I equals to f of x sub I, then the point p sub I, comma, x sub I, y sub I lies on the curve. The part of the surface between x sub I minus 1 and x sub I is approximated by taking the line segment p sub I minus 1, p sub I. Okay, so remember we use this notation with a bar here to represent the line segment, and rotating it about the x-axis. Okay, so if we just focus on this band, let's find the area of that band. And as I extended that right there and right there, so we can see that it's a portion of a cone, right? It's a band from a cone. It's the surface area, partial surface area of a cone. So we can use our formula from before. Okay, so let's let b equal to the surface area of the ith band. Okay, so that surface area right there that we're highlighting it. So we're going to find that surface area for the ith one, and then we can use that formula to expand it out to the entire shape, and then we'll be able to get a good approximation for the area of the entire shape. Okay, well, we just discovered from right above that if we have a cone and we want to find the area of a band, that's what this little formula up here was for. That was the work that we did earlier, that if we have a cone and we just want a band, right? So this is what, when we say band, we're talking about this surface area. The surface area of this blue part, so a partial surface area from this right cone, we saw that this was the formula. Pi L times R1 plus R sub 1 plus R sub 2. So we need these two radiuses. Okay, so if we take this exact same image and rotate it, we'll get exactly what we're working with right now. Okay, so if I took the exact cone we were working with before, copied it down here, tilted it, we see that we have a very, very similar situation. We have a cone, and we're interested in this band over here. So before it was this blue band over here, and now we're interested in this red cone, and we're interested in this red band, which is exactly the same thing. So earlier we found that the area of this band here, the surface area of this band is equal to the formula pi L and then R sub 1 plus R sub 2. Okay, very, very similar to this, except instead of having R sub 1, for us now we have, and this guy here is Y sub I minus 1. And then this guy here, instead of having an R sub 2, we have an a Y sub I. Y sub I. And then here, instead of having L as this distance, well, we have this P sub I minus 1, P sub I, which we recognize from the previous section, right? To find that distance is that the notation that we use is this, right? So the part of the surface area between x sub I minus 1 and x sub I is approximated by taking the line segment P sub I minus 1 to P sub I and rotating it. Okay, so then using this style of notation, then we can say that that surface area then is equal to, I'm just going to use, let's just use B to represent the area of this span. So then that surface area, B, is going to be equal to B, then equals to pi, that stays the same. Now instead of L, we're going to use this notation. And then these guys, well, they're the sum of these two. So it's going to be equal to, and I guess the order doesn't matter, but y sub I minus 1 plus y sub I, parentheses, and then p sub I minus 1, p sub I, right? That line segment. This is the L. I just kind of switched it around a little bit. This is the L. This is the R sub 1 plus R sub 2. Good. Okay, so now, as we said, y sub I is actually the result of evaluating our function at x sub I, and y sub I minus 1 is the result of evaluating our function at x sub I minus 1. So I'm going to replace those two right there. And so we'll get that the band, the surface area of that band, B, is pi times f of x sub I minus 1 plus f of x sub I, and then also evaluated as p sub I minus 1 to p sub I, right? That line segment there. Okay, so now focusing on this segment from, let's see if we can highlight it, this segment again here from x sub I minus 1 to x sub I, remember that we're thinking of delta x being some very, very, very small value. For delta x, very, very small, we're going to let some sample value be chosen between there. So we're going to let some value, I don't know, maybe say somewhere around there, right there. We're going to say that that's equal to some, there, that's equal to some x sub I star. Remember, we need that star notation. It's a sample point. So let x sub I star be a sample point selected from x sub I minus 1 out to x sub I. Good. So keeping in mind that delta x is very, very small, then we would say that x sub I minus 1 and x sub I are going to be very, very close to this sample point x sub I star, right? They're all going to be squished together. For example, like let's just say x sub I minus 1, just to throw a number out there. These numbers don't mean anything, it's just to prove a point. If x sub I minus 1, maybe this is the number 7, and then over here, x sub I, remember that the delta is supposed to be tiny little delta, tiny, teeny little delta. Delta x is going to approach an infinitely small number eventually, but we think of it as being very small. Maybe we want to partition the values between a and b to 1,000 little pieces, 10,000 little pieces, 1,000,000 little pieces, right? Something very, very small. So if this is the number 7, just to throw a number out there, then maybe this one would be the number 7.00000001. And so when we choose a value somewhere in here, that's the sample point, star, sub I, the ith sample point, somewhere in here, well, in order to be in there, it would have to be some like 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, maybe something like that. I mean, that's what it would take for it to be somewhere in there. Lots of tiny little values. And in fact, actually, this is probably, wondering, well, why does it look like that? Actually, it's probably closer to over here, isn't it? But you get my point. In order for it to be somewhere in this, we'd have to go even further. Lots more zeros, and then we'd get somewhere inside here. But either way, I mean, they're all really close to 7, right? This one's really close to this one, and both of them are really close to that one. So when delta x is very, very small, we're going to say that x sub I minus 1 is approximately equal to x sub I, which is approximately equal to x sub I star. Good. And likewise, their outputs, right? Since their inputs are all so close together, we're also going to say that f of x sub I minus 1, the output that you get when you evaluate our function at this point, is going to end up being really, really close to, we'll say and f of x sub I are both going to be very close to f of x sub I star. right? That sample point. They're all close together. So again, we could say that approximately f of x sub I minus 1 is approximately equal to f of x sub I, which is approximately equal to f of x sub I star. Okay, so let's focus on this formula over here. And let me erase this little thing here. I was just making up some numbers to prove a point here, but these numbers have nothing to do with this problem. So let me erase this whole thing here. And so now from the previous section, we remember that this can be approximated by the formula 1 plus f prime evaluated at I star, the sample point, and then all of that gets squared, and then square root of all of that, times dx. And then these two, well, as we just said, f of x sub I is approximately equal to f of x sub I, which is approximately equal to f of x sub I star. So both of these two really just become f of x sub I star plus f of x sub I star. And then there's a pi here, and then there's a b there. Well, these two are the same thing, so we can just say there's two of those. So the band becomes pi times 2, so let's put a 2 in front, becomes 2 pi f of x sub I star times square root of 1 plus f prime of x sub I star squared dx. Okay, so let me compact some of this information over here so I can make some room to organize this new formula and then how we're going to go to the next stage. So let's say for, say this right here. So delta x is, very small. And so we're leading to this conclusion here that x sub I minus 1 is approximately equal to x sub I, which is approximately equal to x sub I star, right? So this information here. Because delta x is very, very small, then x sub I star chosen somewhere in that delta x means that approximately all 3 points are pretty close together. They're almost the same point. So I'm just, compacting all that information into that line so I can erase all of this. And then likewise, because this is true, then we could say that their outputs are also going to be approximately equal to each other. So again, I'm going to just erase all of this and then rewrite it right up here. Comma, and it means that f of x sub I minus 1 is approximately equal to f of x sub I, which is approximately just equal to f of x sub I star, the sample point. Good. And notation-wise, remember that notation-wise, that would also mean that y sub I, this guy right here, we also noted it as y sub I, that height, which we represented it as our radius, right over here. Y sub I is that height. That's this. And then this one, well, then that one is y sub I minus 1. So we'd refer to this guy as some y sub I star. Okay, and so they're all approximately equal to each other as well. Okay, so now let me write down that equation that we just discovered. So capital B is the surface area of a band. So let capital B be the surface area of the ith band, and we just discovered that that surface area B can be written as, or approximated to be, 2 pi f of x sub I star times 1 plus f prime of x sub I star, and then all of that gets squared, square root of all of that, and then delta x. Of course, this is an approximation. I shouldn't have said it equals that. That surface area is approximated by these. And the approximations, well, as you can see, we made a whole bunch of approximations to reduce our formula to this guy. But once we have an approximation for one band, then we can find an approximation to the surface area we're interested in. So the entire area of surface is again approximated by adding up n of these guys. So it'll be a Riemann sum as I ranges from 1 to n, and then this goes right in here. So this is going to be equal to 2 pi f of x sub I star times 1 plus f prime of x sub I star squared, square root of the whole thing, and then delta x. Good. Okay, so that's when we do n partial bands, right? So if we keep going, let's zoom out one more time. Let's come back up here. So this is just one band, but if we do this n different times and then find all those, the surface area of all those individual bands and add them together, then we would get this approximation, right, where it would be kind of like this shape but made up of all flat panels, and that would be all of these surface areas. That's not very, it doesn't seem like a very fun formula to actually figure out with any number of them, right? Even if it said do it for 6, that seems like it would be kind of a pain to break it up into 6 pieces and then add them together. Luckily, this looks an awful lot like something that would get better. This approximation would get better and better and better as n goes out to infinity. And as n goes out to infinity, we would no longer have an approximation. At infinity, if it exists, we would have the exact surface area we're interested in. Okay, so the surface area now, the area of the surface, area of the surface of our shape is going to be exactly equal, no longer an approximation, exactly equal to the limit as n goes to infinity of this sum. I goes from 1 to n of 2 pi f of x sub I star, and then 1 plus f prime of x sub I star. The whole thing gets squared, and then square root that whole thing, delta x. And this we might recognize from our definitions of integrals. This is exactly equal to the integral from a to b as x ranges. I like putting the variable myself here, but so as x ranges from a to x ranges to b of exactly this. So this would be equal to 2 pi f of x times 1 plus f prime of x squared, square root of that whole thing, dx. Good. So this is the integral that would give us that surface area. Let me zoom out and look at the whole thing. Okay, so the surface area that we're looking for is equal to the limit as n goes to infinity of this Riemann sum, which can then be identified as an integral. And so here is our formula. Finally, we've achieved our formula. This integral will tell us the surface area of a smooth curvature that's achieved when a function f of x is rotated about the x-axis like we've been trying to get. Okay, so finally, um, if we have a case where f is positive and has a continuous derivative, we define the surface area of the surface obtained by rotating the curve y equals to f of x from x ranges from a to b about the y-axis. In other words, getting this exact same sort of shape, and kind of keep this in mind, some surface, some function f of x rotated about the x-axis, assuming f of x is positive, of course. Otherwise, we'd end up with something weird. Um, and this is the exact equation we'd get. So there's a whole lot of work to get something that looks pretty straightforward, right? So this part of it looks exactly like the equation that we worked with in the previous section, which gives you the length of a line set of a curvature, right? So the length of just that red curvy thing was the integral of this, and then 2 pi is a constant, and then f of x. This almost looks like 2 pi r, right, where f of x is constantly the r for any one of these circles. So if you think of it as infinite number of circles, this is like the area of a circle, and then this is like the length of this curvature here. So it almost feels a lot like the surface area of a cylinder, for example, where you'd find the circumference of a circumference of a circle and then multiply it times its height. This almost feels the same way, right? Where this, if you think of some circle, this could almost look like the surface area, the circumference of one circle, where f of x represents the radius of it. Right here, let me write down what I mean. And if we think of some random circle in the center of this, say something like this, right? We can think of this circle, the circumference of that circle, the circumference is equal to 2 pi r, where r in this case, well, that would be this. So 2 pi f of x for some x value there, and then this height right there would be the f of x. So it's like the circumference multiplied by the length of our shape, of our picture, which again reminds me a whole lot of the case we saw at the very beginning when we had a simple cylinder looking thing like this and we wanted the surface area. We saw that it was the circumference of the circle multiplied by its height. So this formula is very familiar. So even though it was a lot of work to get to this final result, the final result seemed to kind of make intuitive sense, and it's actually not that difficult to work with, assuming, of course, that f of x is a suitable function that is differentiable, that we can find that derivative, and that we can plug it into this little formula, and that's an integral that we can integrate. So if all those things work out, if f of x is a nice function we can work with, then this shouldn't be too bad. Let's look at an example. Okay, so example 1, let the curve y equals to the square root of 4 minus x squared be our function. And we're interested as x ranges from -1 to 1. So this is an arc of the circle x squared plus y squared equals to 4, right? In other words, if we solve for y here, so square both sides, we get y, add x squared to both sides, we end up with this equation. So we see that this is a little arc from a circle of radius 2. Okay, so find the area of the surface obtained by rotating this arc about the x-axis, right? So this is the shape we get. So this little red little arc here, this is the equation y equals to the square root of 4 minus x squared. And so it kind of looks like a hockey puck, right? And we want the surface area of just this part, not the circles at the edges. And so we're going to use our formula. So our formula for the surface area S was equal to the integral from a to b of 2 pi f of x times, and then it's 1 plus f prime of x squared, square root of that whole thing, dx. Notice that another equivalent notation is to not use the function notation, which would be to use this y. So I could also say that this surface area is the integral from a to b of 2 pi y times, and then 1 plus, and then instead of using this function notation, I could say that this is dy dx squared, and then square root of that whole thing, dx, right? Same thing, just different notation styles. Either way, we know we need the derivative. So let's find that derivative. So I have that y equals to square root of 4 minus x squared. So the derivative with respect to x of the y is equal to the derivative with respect to x of the square root of 4 minus x squared. So that means that dy dx is equal to, and I'm going to rewrite this in terms of 4 minus x squared to the power of positive 1/2. And we want the derivative with respect to x on that one. So that means that dy dx is equal to 1/2 4 minus x squared to the power of negative 1/2 times the chain rule. Scroll over here. The chain rule says that now I also have to multiply this times 4 minus x squared, the derivative of 4 minus x squared. So dy dx, my derivative will be 1/2 4 minus x squared to the power of negative 1/2 times negative 2x. That simplifies a little bit, so that means that dy dx is going to be equal to, this guy cancels with this, so this 2 cancels with that guy, and so I'll just have a negative x in the numerator divided by this, which is going to be 4 minus x squared to the power of positive 1/2, or negative x divided by the square root of 4 minus x squared. Right, either way, we found our derivative. And so that formula right there is the one we bring over here and square it. So let me scroll over here. So now back to this equation. So s is going to be the integral from, and now x is going to range from negative 1 to positive 1. Let me scroll up here. Right, x ranges from negative 1 to 1. And then this is just the constant, 2 pi. And then y, well, that's this guy right here. So it'll be times the square root of 4 minus x squared times, and then it's the square root of 1 plus, and then the derivative squared, and then that derivative is this, so that'll be minus x over the square root of 4 minus x squared, and then that whole thing gets squared, and then that's our integral that we need to simplify. Looks pretty messy, but it actually works out really, really nicely. So if we focus on this part, we have negative x squared. That's just going to be x squared. And then in the denominator, we have the square root of 4 minus x squared. So when we square it, that just simplifies as well. So this is going to be equal to s is equal to, I'm going to pull out that 2 pi out here, 2 pi, integral from negative 1 to 1, and then this is 4 minus x squared times, and then here I'm going to simplify this to be 1 plus x squared all over 4 minus x squared. All of that is still inside this root, and then we still have a dx there. Okay, to get a common denominator here, I'm going to multiply the numerator and denominator, right? Create a fraction that has a 4 minus, let's make some space here, 4 minus x squared divided by 4 minus x squared. That's another version of 1. So then they have the same denominator, and I get to bring it all under one big happy fraction. So we get 2 pi integral from negative 1 to 1 of the square root of 4 minus x squared times, and then this becomes 4 minus x squared plus x squared divided by 4 minus x squared. And all of that is still inside the root, dx. Now these guys cancel, and then I can simplify this. So this is our surface area. Oops. So this is our surface area S. So S then equals to 2 pi integral from -1 to 1 of the root 4 minus x squared times, this can be broken down into the square root of 4 divided by the square root of 4 minus x squared dx. And so now, luckily, all of that reduces, and the square root of 4 turns into positive 2. And so all of that then simplifies to give me that my area S, surface area S, is 2 pi integral from -1 to 1 of just 2 dx, which we know can be simplified to just be 4 pi integral of 1 dx. Pull this over here. Say that S then is equal to 4 pi integral -1 to 1 of just 1 dx, which we know that S then is equal to 4 pi times x. Derivative of x is just going to equal to 1. Evaluate it from -1 to 1. So S equals to 4 pi times 1 minus -1, becomes that S equals to, well, I'll just put it here, S equals to 4 pi times 2, or the surface area just equals to 8 pi. Okay, and that's our answer. Erase this guy. Okay, so not too bad, right? It starts off pretty ugly, but for certain equations, things work out nicely. Of course, we have to have an equation whose derivative is not too bad, and then when we plug it into this equation, hopefully we'll run into cases like this one where things just kind of unravel and cancel, reduce, and you get to something manageable. Now, might not be quite as easy as this one, but hopefully it's not too bad. Otherwise, if it does become something kind of ugly, at least we have an equation for it. We know what integral we want to find, and then you might be asked to use computers or some sort of technology to help you find that answer, to integrate something that's too difficult to do by hand. Okay. Okay, so here are some of your homework problems. For 1, 3, and 5, oh, I think I just assigned 3 and 5. So for 3 and 5, only do part A. Don't worry about the second part where you use a calculator to approximate it. Just set them up. So set it up for the x-axis, set it up for the y-axis, rotating about the y-axis. And then I assigned some questions over here, 7 through 17 odd. So let's do a couple from one from here and one from there. We'll figure out how we rotated about the y-axis. Okay, so how about number 10? Let's do number 10. Okay, so we're interested in figuring out the surface area of the shape created by rotating this about the x-axis. So let me just start off by writing down my formula. I know S is going to be equal to the integral from A to B of 2 pi y times 1 plus dy dx squared, square root of that whole thing, and then dx. Okay, so the y, I got that. So I got to figure out what this whole thing is right in here. So let's figure out the derivative, and then let's figure out what the square root of 1 plus the derivative squared is. So let's come over here. So let's find the derivative. So I'll use the notation y prime is equal to the derivative of this, d dx of the 1 plus e to the x square root of that whole thing. Okay, so y prime is equal to d dx of 1 plus e to the x raised to the power of positive 1/2. So y prime equals to 1/2 1 plus e to the x raised to the negative 1/2. And then chain rule, multiply it times the derivative with respect to x of the 1 plus e to the x, which means that y prime is equal to 1/2 1 plus e to the x raised to the power of negative 1/2 times, and then the derivative of this is just going to be an e to the x. So y prime is equal to a giant fraction where we have an e to the x in the numerator and a 2 and a 1 plus e to the x square rooted in the denominator. Okay, so that's our dy dx, right, otherwise known as dy dx, which is equal to y prime, which is equal to this. So now let's figure out what this part is right here. We need to find the square root, 1 plus the derivative squared, and then the square root of that whole thing. So let's see, 1 plus dy dx squared, and then square root of that whole thing, is equal to 1 plus, and then the derivative we just said was e to the x over 2 square root of 1 plus e to the x, and then that whole thing gets squared, and then that whole thing is inside this root, which then becomes, well, there's two of these, we're squaring this guy, so it becomes 1 plus e to the 2x divided by 4, and then 1 plus e to the x. Right, squaring this guy, squaring that guy, squaring that guy, everyone gets squared. There's a plus 1, square of that whole thing. Okay, common denominator is going to be this guy. So let's change this 1 to be a 4, 1 plus e to the x divided by the same thing, 4, let me make space here for this guy, 4 times 1 plus e to the x, and then there's a plus sign here. Right, so this is another version of 1. The numerator is identical to the denominator, and so now we can tuck it all under one big happy fraction and say that this is 4, 1 plus e to the x plus e to the 2x all over 4, 1 plus e to the x. All of that gets square rooted. So now distributing this 4 goes there, this 4 goes there, distributing it, we get 4 plus 4e to the x plus e to the 2x all over 4, 1 plus e to the x. All of that still inside that square root. Okay, let's make some space over here. So this is going to be equal to e to the 2x plus 4e to the x plus 4 all over 4, 1 plus e to the x, and then all of that is inside this root. Do it again. Okay, well, this is just the quadratic in disguise. Think of it as, say, u equals to e to the x. Then this is u squared plus 4u plus 4. This is u squared plus 4u plus 4, which we know becomes u plus 2 squared. Good. So that's how we can factor this guy. And so we get that this is e to the x plus 2 squared all over 4, 1 plus e to the x, and then that whole thing is inside this root, not squared. And then that simplifies to just give me e to the x plus 2 divided by 2, and then square root of 1 plus e to the x. Okay, so remember this whole thing was just to figure out this, right? That's where I started. Let me zoom out a little more. Okay, remember that this whole thing was just about figuring out this part right here. I haven't integrated anything. I just figured out that this part right here, which is this, um, simplifies to that. Okay, so now let's figure out the actual integral. So now taking the integral, I already have this part. All I have to do is multiply it times y, which is this equation, times 2 pi. So now let's figure out the actual integral. So s is equal to the integral from a to b, which is from 0 to 1, 0 to 1 of 2 pi times y, which is this equation, square root of 1 plus e to the x, times this guy, which we just established is this, times e to the x plus 2 divided by 2 square root of 1 plus e to the x dx. Right? So this whole thing here, this was that. Right? We first found the derivative, squared it, added 1, took the square root, and that's how we got that whole thing. Okay, let me unlight. Do that. All right, let me zoom over here. So now this is luckily going to reduce quite a bit. This 2 reduces with that 2. And this whole root, the square root of 1 plus e to the x power, cancels with that guy. And so this whole thing just simplifies to become, let's pull out the pi out in front, integral from 0 to 1 of e to the x plus 2 dx. Okay, so we know that that's going to become pi times e to the x, the derivative, the antiderivative of e to the x is just e to the x, plus 2x evaluated from 0 to 1. So this becomes equal to, let me erase this guy, this becomes equal to pi times e to the first power plus 2 times 1 minus e to the 0 power minus 2 times 0. So e to the first power, that's just e. 2 times 1, well, that's just going to be 2. E to the 0 power, well, that's just going to be equal to 1. And that's just 0. So we get plus 2 minus 1 becomes plus 1. So this is just going to be equal to, so s equals this, s equals that. So now s just equals to pi times, and then e to the power of 1 plus 1. Okay, and so that's our answer. Okay, now let's try something like number 18. Given this equation, y equals to 1/4 x squared minus 1/2 ln x, where x ranges from 1 to 2 inclusive, rotate about the y-axis and find the area of the resulting surface. Okay, so far we've always been working with rotating about the x-axis. This is rotating about the y-axis. So the formula for working with rotating about the x-axis, the y-axis looks like this. Okay, so this is the formula we've been working with so far. We've been given some equation, y equals to f of x, for x being defined from a to b along the x-axis, and we're rotating it about the x-axis, and this is the formula we've been working with. Okay, so now if we want to rotate an equation about the y-axis, then this is the formula we're going to work with. Very similarly, so we have an integral of 2 pi x ds, where the ds is equal to either this one or this one. So we kind of have a choice, and the difference being whether you want to take the derivative with respect to x. So if we have some function y equals 2 written in x, and we want to take its derivative with respect to x, we can use this version of it, and then we'll take a derivative with respect to the x, or we have the option of also doing this. I haven't really talked about why you have this freedom, and we're not going to prove it. We just get to use it. Okay, so you have that choice. We have that freedom here. You just have to be careful that they match. If you take our equation, you take a derivative with respect to x, then we have to differentiate with respect to x, which means that our limits of differentiation must also match. And also over here, if we take a derivative with respect to y, then we have to integrate with respect to y, and also our limits of integration must also match. Okay, so let's do number 10. Okay, so for number 18, they gave me the equation in the form of y equals to something in x, and I can see that taking the derivative is going to be pretty easy with respect to x. So dy dx is pretty easy. They also define x to range from 1 to 2. So it looks like this is the version of ds that I want to use. So I'm going to use this integral, and I'm going to let the ds represent this here. Okay, so let's create this. I need to find the derivative with respect to x. So dy dx is equal to the derivative with respect to x on the 1/4 x squared minus 1/2 ln x. Zoom into here a little bit. So now this derivative, dy dx, is going to be equal to 1/4 times 2x to the first power minus 1/2 times 1 over x, which then reduces. Dy dx then becomes x over 2 minus 1 over 2x. Okay, so that's our derivative. Next, we want to think about the 1 plus dy dx squared. And I know all of that is going to go inside this root. So let's think about what that looks like. That's going to be 1 plus, and then x over 2 minus 1 over 2x. All of that gets squared, and inside that radical. And then foiling this out, we get 1 plus, and then the pattern for foiling it is going to be x over 2 squared minus 2 times x over 2 times 1 over 2x plus 1 over 2x quantity squared. That's just foiling this guy out, and then I take the square root of all of that. Okay, simplifying that a little bit more. So this is going to be equal to 1 plus x squared over 4 minus, okay, a bunch of stuff reduces here. So we'll say this guy reduces with that guy, this x reduces with that x. So this whole thing right in here just turns out to be minus 1/2. Minus 1/2 plus, and then this becomes 1 over 4x squared. All of that is inside this root. Okay, so 1 minus 1/2 just becomes positive 1/2. So this becomes x squared over 4. I'm going to move these things around, plus 1 over 4x squared plus 1/2. All of that is inside that root. Okay, let's get a common denominator and bring this all together under one big happy fraction inside the root. So we're going to multiply this fraction by a x squared, and this one we'll leave alone, and this one needs to be multiplied by a 2x squared over 2x squared. So we'll end up with x to the 4th power plus 1, so we'll say plus 1 plus 2x to the 2nd power, all of that over 4x squared. All that's still inside this giant root. And now this looks like a quadratic in disguise here. So let's put x squared squared, that's really the x to the fourth, plus a 2x squared plus a 1. So this, if we did like a u substitution, we let u equal to x squared, this would look an awful lot like u squared plus 2u plus 1, which we know factors into u plus 1 squared. So that's what that's going to simplify as. And then in the denominator, we have this 4x squared, square root of that whole thing. So this becomes x squared plus 1, parentheses, squared, all over 4x squared, square root of that whole thing. And so now we can simplify it to just be x squared plus 1 divided by 2x. Okay, so we're almost there. We want to find this surface area, and we just figured out what this whole thing is. This whole thing, the square root of 1 plus dy dx squared, is equal to just this here. So let's set up our integral. S is going to be equal to the integral, and then I'll set up the limits in 1 second. This is going to be 2 pi x, and then the ds I've chosen is this one, which is equal to 1 plus dy dx squared, and then the square root of all that, and then dx, like that. And so if I'm taking the derivative with respect to x, that means that this x must range from, and we were told x ranged from 1 to 2. X ranges from 1 to 2. That's the integral we want to solve, except we just figured out what this whole thing is right here. This whole thing simplifies to just be this. So I'm going to just substitute it right in there and get that my surface area of interest is the integral as x ranges from 1 to 2 of 2 pi x, and then there's this fraction with a x squared plus 1 divided by 2x dx. Okay, I'm going to zoom into here a little bit. This reduces quite a bit. The x cancels with this x, this 2 cancels with this 2, and so I can pull the pi out and say that s is equal to pi integral as x ranges from 1 to 2 of just x squared plus 1 dx, which means that s equals to pi, and then this is just going to be 1/3 x to the third power plus x evaluated as x ranges from 1 to 2. So s equals to pi times 1/3 blank cubed plus blank minus, and well, actually let's put parentheses here, so this is that, and then minus, and then 1/3 blank cubed plus blank, close that parentheses, and put another parentheses out here. Okay, so then we had 2 goes in here, 2 goes in here, and 1 goes in here, 1 goes in here. So we just have to carefully simplify that. So s equals to pi times, and then this is going to be 8 divided by 3 plus 2 minus, this is going to be minus 1/3 minus 1. Okay, so the 2 and the minus 1 just becomes plus 1. So this becomes s equals to pi, parentheses, that's going to be 8/3, well, 8 minus 1 becomes 7. Let's make that 7/3. 7/3 plus 1. And then that plus 1 can be written as a 3/3, 3/3, which then will lead me to 10/3. Right? So this equals to pi times 10/3, and that's our final answer. So let me zoom out. So this is our final answer here. So S for us will be equal to 10 pi divided by 3. 10 pi divided by 3. Okay, now just to get a sense of what this graph looks like, let's go over to Desmos. Okay, so here's what the graph looks like. Remember that the domain of the ln function is positive numbers, so it's only defined from 0 forward, not including 0. This is what the entire graph looks like. Of course, we're only interested in the segment between 1 and 2, so this little part here between 1 and 2, so just this portion of our graph. Yeah, put that in here. So just that portion right there. And then we're rotating about the y-axis. So we're going to take this guy and rotate it about the y-axis. See if I can draw that a little bit. Okay, so this is the general shape. It almost looks like a saucer. It's open at the top, open at the bottom, and we're just interested in the surface area around the skin of this thing, around the edges. Okay, and so we established that that surface area was 10 pi over 3 units. Right, that surface area in blue right in there. Okay, good. That should be more than enough to complete your homework. Please stop by my office hours if you have any questions.